G'day chemists, welcome to day 9 of IB question of the day as we lead up to our IB chemistry question paper for the November time period. A couple of my students, one of my students in particular, has asked for us to focus on some paper 2 style questions. So for this week in particular, we'll be focusing on paper 2 style questions. There are, as of when this is published, there'll be 21 days left until your exam. So with all that, let's jump into our question of the day. So paper 2 means that there are bigger questions, multiple part questions that relate to one another, and that's pretty interesting. So pause this video here and we'll read through the paper, read through the question, and then we'll go through it together. Alrighty, so our 6-mark question here. We have all 6 marks here. We won't have all of the marks in all of the questions. A monoprotic acid, HX, is found to have the following composition by mass. There's 39.99% of carbon, 6.73% hydrogen, and 53.28% oxygen. Determine the empirical formula of the compound. Then you're given an amount, 225 centimeters cubed, or 25 milliliters, of the solution containing 1.51 grams of our acid, HX, is titrated with a 0.750 moles per liter solution of sodium hydroxide. The acid, the HX solution, is exactly neutralized by 22.30 centimeters cubed or milliliters of the sodium hydroxide solution. Determine the molar mass of HX. So we've got a molar mass question there. State the formula, molecular formula of HX, which will be different to the empirical formula there. HX reacts with aqueous sodium hydroxide according to the equation. HX plus NaOH gives you NaX plus H2O. Identify the functional group present, a functional group present in HX. What a fun question. Okay, so let's have a look. We'll do each part by part and we'll go through all of them and we'll work it out. So here's our work solutions. Alrighty, so for part A, determining the empirical formula. That is the important part, the empirical formula. You need to know what that is of HX. And in that X, we know that the X is at least partially oxygens and carbons. It's very likely that it's also some hydrogens as well, but we know it's at least some carbons and oxygens. Okay, so the formula we're going to use here to start off with is N equals mass over molar mass. You're going to see different versions of that. For example, molar mass down here is represented as straight capital. That's what the IB does. I tend to, because I come from various other systems as well as teaching the IB, I prefer M with a little subscript R, whatever, it doesn't matter. It's not going to affect you in the slightest. Just know what they mean. And then we are also going to, and something else we could, so N equals mass over molar mass. We don't have masses here, but we can use the percentage as grams for our equations. And we just assume that you have 100 grams of the whole thing. And then, therefore, if you get 100 grams, 6.73% of that is 6.73 grams. Okay, MR we get from the periodic table, so this is where we find the information, and moles is what we're going to then calculate. So, M1, there's a 2-mark question. Mark 1 comes from the moles of each element present. Remember, using percentage as grams. So that means you need to get the moles of all 3 before you get the first mark. And then the second mark comes from using those to get the ratios of elements to give you the empirical formula. Remember, an empirical formula is the smallest possible ratio of each element stuck together, right? So let's have a look. All right, first off, the moles of carbon, I was about to say calcium, the moles of carbon mass over molar mass, 39.99 grams over 12.01 gives us 3.33 moles. We do the same for hydrogen, 6.73 over 1.01. Remember, that comes from the periodic table, which is in your data booklet. That gives us, it's only a hundredth as evil as it could be, 6.66 moles. And then we go the moles of oxygen, again, mass over molar mass, 53.28 divided by 16, gives us 3.33. Now, what we get to do with that is we can just work out the ratios. Lots of different ways to do it. So carbon 3.33, hydrogen 6.66, oxygen 3.33. What is the number that these can all be divided by? I would say 3.33. So the way to do it is just sort of divide it by the lowest number. So the lowest mole over here is 3.33. So if we divide all of these by 3.33, that should get us our numbers, which will be 1 for carbon, because 3.33 divided by 3.3 is going to be 1. 6.66 divided by 3.33 is going to be 2, so H2, and again, O1. So CH2O. That's our answer for that one. That's our empirical formula. And then we go, yes, this is what we do to get mark 1. This is what we do down here to get mark 2. Alrighty, so part B. A 25 centimeter cube solution containing 1.51 grams of HX is titrated with 0.75 moles per liter of sodium hydroxide, exactly neutralized by 22.3 milliliters of sodium hydroxide solution. Determine the molar mass. Okay, so we've cleared ourselves some space. So we're after the molar mass. That is our target. So what equations are we going to use? Well, first off, we're doing a titration. Okay, so that means we're going to use some concentration. But molar mass is our target. So one of our assumptions is that HX is monoprotic. Okay, otherwise it would be H2X. That's how it would be written. So HX is monoprotic, which means and sodium hydroxide gives off one hydroxide group, not hydroxyl. So that means the ratio of sodium hydroxide to acid is 1 to 1. Okay, so part of the molar mass formula is moles. All right, so that's how we'll work out that. And we want to get our moles of sodium hydroxide, so we know how many moles of this we have, from the concentration equals moles over volume. So once we calculate the moles of sodium hydroxide, we can calculate the moles of our acid, and again it's got that 1 to 1 ratio. And from there we can calculate the molar mass using mass over molar mass, and so on. Where do we get the mass from? Well, it's right in our question over here. It's given to us. So, first mark out of 2. That's a lot, by the way, for 2 marks. This is a pretty hectic question. We get moles of HX. That's our first mark. And our second one comes and gives us the molar mass. So if you just worked out the moles of sodium hydroxide, you would get no marks. You need to convert that to the moles of HX. It's important with the IB in particular to know where your marks are coming from. So C equals sodium hydroxide over volume. Moles of sodium hydroxide therefore equals concentration times volume. Remember, the moles is our target in this particular step. So it becomes 0.750 moles per liter times the volume, which is 0.02230. So remember, you've got to convert this milliliters into liters, or centimeters cubed into decimeters cubed. So then we go to 0.0167 mole. So that's how many moles of sodium hydroxide we have. We haven't got any marks yet, but we know that the ratio of moles of sodium hydroxide is the same as the moles of HX. Therefore the moles of HX is 0.0167 moles. And it is important that you write that down. because, you know, that's where our mark's coming from. So we want to write all our working out down. So now that we know how many moles of this acid we have, we can go moles equals mass over molar mass. Therefore, we can rearrange that so that our molar mass of HX equals mass divided by moles, just simple rearranging the equation. So it's 1.51 grams over 0.0167 mole from the previous part, gives us 90.4 grams per mole. There's M1 and there's M2. So we've now got our answer for that one. Alrighty. Next question. So we now need to state the molecular formula of HX. Molecular formula. So this is no longer the simplest ratio. This is what's going on. And that means it's going to be a multiple of our empirical formula. So it's going to be a multiple of CH2O, right? So they're always going to stay in that ratio, just with larger numbers. Potentially the same number, but larger numbers. Alrighty, so we get 1 mark. That's it for the correct formula. So we know the molar mass of CH2O, right? We can calculate that. So 12.01. Again, this comes from the periodic table. Plus 2 times 1.01 plus 16 gives us 30.03 grams per mole. We know from our previous question that the molar mass of HX is 90.4. So that's close enough to 3, right? So if we divide that 90.4 divided by 3, that means we now need to multiply our empirical formula by 3, which gives us C3H6O3. Now, this is not an exact number, and that's an important thing to realize, that you won't get often the exact number. The reason is that the data from the previous question comes from practical, right? Like there's practical limitations within that. So that's why the answers aren't quite exact. All right, next question. HX reacts with aqueous sodium hydroxide according to the equation. Boom, boom, boom. So neutralization reaction. Identify a functional group present. Oh, sorry. That's where our mark one goes wrong. Functional group. We're looking for the functional group in this organic acid. Organic acid is your clue. Okay, so neutralization. HX is therefore an organic acid. We can only get the mark for correctly identifying the functional group. And it is a carboxyl COOH. Now, if you have a look up here, there is another O, right? But there's only one other O, so that means it's not diprotic. We know it's not diprotic as well because it's HX, not H2X. So we have this, like, there's another oxygen there, but we can't really determine what that is. It could be various things. So we just identify the carboxyl, the COOH. Both of these were accepted as correct answers, by the way. I would have used the word carboxyl and then written COOH next to it. Yeah, okay. So that's that. Now, as I said, there's another oxygen atom, but we can't determine exactly what that would be. All right, so what are our key takeaways here? We need to understand the relationships between different chemical formula, empirical and molecular formula. We need to be able to move between stoichiometric values here. So concentration to moles, molar mass, volume, mass. Just remember, the center of all of those calculations always is moles. So you should always come back to moles. Like that's your center point, right? If you need to get from concentration to molar mass, you have to go via moles. If you need to get to mass to concentration, again, you're going via moles in the middle there. And these are the equations we use for that. You need to be able to link concepts in here. Like here we need to be able to link in one question, organic structure, acids and bases, stoichiometry. It was really important there, right? To be able to link the concepts. And that's what happens in paper. All right, so if you have any questions, put them in the comments below, or if you're one of my students, just send me an email. We'll get back to you as quickly as we can, and we'll be responsive. If you have other sorts of questions you'd like to see, please let us know. And yeah, hit the subscribe so you can keep up with it. I don't know, throw us a like, why not? And yeah, we'll see you next time. I'll see you tomorrow. Okay, bye now.